All right, I'm going to go ahead and get started. This is the Math 2415 weekly review, and here's my cat Ember. So today I am going to talk about cross product. And this is 12.4, chapter 12.4. And this is the next topic are going to be lines. And this is 12.5. If I get to the end and I find I have some more time, I might talk about planes a little bit. I don't think this has been covered in lecture yet, though. So anyways, let's get started. So the cross product, one way to calculate cross product would be to have, if we have two vectors, u and v, the magnitude of the cross product is equal to the magnitude of u times the magnitude of v times sine of theta, where theta is the angle between these two vectors. The cross product is similar to the dot product in that it is a way to multiply vectors. But the only difference is we have a vector output. As opposed to the cross product, or to the dot product, we had a scalar, one number output. This is a vector, an entire vector. And what's special about this vector is that it's a vector orthogonal or perpendicular or normal to both u and v. That is, u cross v is perpendicular to u and v. Sometimes when you're calculating cross product, there's some arithmetic to do. And so if you ever get nervous that you messed up, what you can do is take your vector output cross product and take the dot product with u and v, and you should find that all the time u dot u cross v will be 0, as well as v cross u cross v. Because two vectors are orthogonal if and only if their dot product is 0. And we know that from the last time, that was 12.3. So anyways, if we have vector u in R3, u and v in R3 vectors, and we want to calculate u cross v, what we do is we take the convention of a determinant. The first row will be I, j, k. I being 1, 0, 0, j being 0, 1, 0, and k being 0, 0, 1. Okay. And so if the components for u are just, keep it arbitrary, u1, u2, u3, some numbers, and v is v1, v2, v3, then u cross v, we put u in the second row, the components for u in the second row, and then we would put the components for v in the third row. And now we proceed to take a determinant. And if you've never taken a 3x3 determinant before, well, I'm going to show you. So we're going to cross out, we're going to circle I, and that number goes right here. And then we cross out the column and the row, and we're left with this. And we write that as a 2 by 2 determinant. Okay, now we subtract off, circling J. J goes right here. And we cross out the column and the row. And what's left is this 2 by 2 determinant. That is U1, U3, V1, V3. And then we add K, circling K, crossing out the column and the row, and creating the remaining 2 by 2 determinant. We get U1, U2, V1, V2. Okay, so now we have 3 2 by 2 determinants. And to take a 2 by 2 determinant, if we're not familiar, if our components are A, B, C, D, we multiply A by D, we subtract off C by B. So I'm going to do that right here, here, and here. So we have I times U2 V3 minus V2 U3. We have minus J times U1 V3 minus V1 U3 plus K times U1 V minus V1 U2. And if these were real numbers, then I would do the subtraction. But I don't know what they are because I kept it arbitrary. So this is the cross product, U cross V. Notice every time we're going to have I, a 2 by 2 determinant, and then we have a minus. Don't forget this minus J, a 2 by 2 determinant, plus K times a 2 by 2 determinant. This is going to be the form every time. So we're going to do a couple of examples. So example, let's find a unit vector orthogonal to both vectors 3, 2, 1 and -1, 1, 0. Okay, so how do we find a vector orthogonal to two vectors? How do we even do that? Any ideas? Cross product. Now, how would we make it a unit vector? It has to be a special type of vector. We can find a vector, all right, by taking the cross product, but how do we make that a unit vector? Yep, that's right. We divide by the magnitude. So if we call this U and we call this V, our final answer is going to be U cross V divided by the magnitude of U cross V. So this is the answer. Now we actually have to calculate it. Let's go ahead and do that. We have I, J, K. Right, I'm just building my 3 by 3 determinant. If this is U cross V, U would go in the second row, and V would go in the third. Okay, so I have I times, right? Imagine we're crossing out the I column and the I row. We have the remaining 2 by 2 determinant 2, 1, 1, 0 minus J times crossing out the J column and the J row. We get the remaining determinant 3, 1, negative 1, 0. And then I'm going to add K, but just bring it down here, times the 2 by 2 determinant. All right, we cross out this column and we cross out this row, and the remaining 4 numbers make up my 2 by 2 determinant associated with K. All right, so that means we get U cross V is equal to I times this 2 by 2 determinant. We evaluate this, right? We have 2 times 0 minus 1 times 1. 2 times 0 is just 0, minus 1 times 1 is just 1. Remember, the minus is always with the J. And then we have 3 times 0 minus negative 1 times 1. So that's going to be 0 minus a negative 1 is plus 1. And then we have plus K times 3 times 1 is 3. Negative 1 times 2 is going to be a positive 2. Adding all these numbers up, we have 0 minus 1, so this is a negative I. I have a negative 0 plus 1, so that's going to be a negative J. And then we have 3 plus 2, it's going to be a plus 5K. Without the IJK, it would look like negative 1, 5. So this is U cross V. This is a vector that's orthogonal to both U and V, but the question was asking for a unit vector. So let's go ahead and divide by the magnitude. First, let's calculate the magnitude of U cross V. The magnitude of U cross V is the square root of each component. Negative 1 squared plus negative 1 squared plus 5 squared. So this is the square root of 25 plus 1 is 27. Thus, U cross V divided by the magnitude of U cross V is equal to negative 1 over root 27, negative 1 over root 27, 5 over root 27. And I've never found it to be too big of a deal, but if you want to rationalize your denominator, you could say negative root 27 over 27, negative root 27 over 27, regular 27. Here we go, 27, and then we have 5 root 27 over 27. Let's answer. Okay. One cool thing about the cross product is the area of a parallelogram determined by vectors U and V is the length of the cross product of U and V. Now, how in the world do I find the length of a cross product? How in the world do I find the length of a vector, right? The cross product outputs a vector. How do I find the length of a vector? Yep, that's right. Yep. Length is just magnitude. The length of a vector is magnitude. So I could have wrote this: the area of the parallelogram determined by U and V is the magnitude of the cross product. Okay. So this next problem, we are given. This is in R2. We're in the XY plane now. Okay. We're given a parallelogram. You know, by its vertices. And we're asked to find the area of this parallelogram. So the vertices of the parallelogram are given as A is -2, 1, B is 0, 4, C is 4, 2, and D is 2, -1. So first I'm going to draw a picture. I have -2, 1. B is 0, 4. C is 4, 2. And D is 2, -1. So this is my parallelogram. With vertices A, B, C, D. So what this theorem above says is if I create a vector right here and a vector right here, if I take the cross product of these two vectors and I find the magnitude of that vector, then that will be the entire area of the parallelogram. Notice we only have to fix one point. We fix one point and we create a vector coming out of that point to the two other points. Because the cross product takes two vectors, right? And so if we pick this vector and this vector, we're forced to have C to make it a parallelogram. We're forced into this point. So how? Well, first let's calculate these vectors, right? Vector AB, right? It's terminal minus initial. So we have 0 minus -2. That's 2. 4 minus 1 is 3. Then we have vector AD. Vector AD would be terminal minus initial. So we have 2 minus -2 is 4. Then we have -1 minus 1 is -2. And that just looks right. You know, if we look at vector AB, we notice that we go 2 in the x direction and 3 up. Vector AD, we go 2 down and 4 to the right. So it looks good. Now, how in the world do I take a cross product with only two components, a vector with two components? Is it any different? Are you suggesting a 2x2 determinant? Well, if I do a 2x2 determinant, Let's try it. The 2 by 2. Well, I would put, I guess I'd put 2, 3 here, and 4, negative 2. But this just gives me a scalar. That's not right. The cross product has a vector output. Right? I need an entire vector. Now let's think about it. Let's think about this. This is xy. Yeah, we filled the z with zeros because the x plane, if we look at it in R3, then the z component would have to be 0 since we're lying on the xy plane. We're lying on the xy plane. It's like the z-axis is pointing out of the page right here. And so the cross product gives a vector that's orthogonal to both AB and AD. Now, the only way to do that would be to either come out of the screen or go into the screen. So we have our parallelogram. Then we have this and this. Not, it's not exactly the picture. And so the cross product is a vector pointing out like this. It's orthogonal to this vector and this vector. So yeah, exactly. If we take a cross product with a vector in R2 on the xy plane, the output is going to be in R3. The only way to draw a vector orthogonal in 2 dimensions is to have it go to 3 dimensions. Right, and notice what happens. We cross out the I, we cross out I. So we have I times, and then this, I'm going to leave it like this for now. This is 3, 0, negative 2, 0. We have minus j. Now if we subtract off j, we have to put the 2 by 2 determinant, 2, 0, 4, 0, plus k times the 2 by 2 determinant. Two, 3, 4, negative 2. So what do you notice about this determinant? We have 3 times 0, negative 2 times 0. That's 0i. 2 times 0, 4 times 0, plus 0j. Well, I don't know if it's plus yet. Negative 4 minus 12. So our vector output is 0, 0, negative 16. I'm going to give you a little trick for determinants. I guess we learned this in linear algebra, but a determinant with either a row or column of all zeros is 0. Notice what happened right here. We had an entire column of all zeros, so the determinant is going to be 0 automatically. We have an entire column of all zeros. It's going to be 0 automatically. We just know that. Same thing with the 3 by 3. If we have like a 3 by 3 determinant, this is like A, B, 0, 0, 0, C, D, F. This equals 0. You could calculate this by doing the cofactor expansion, but since we have a column of all zeros, the determinant is 0. Okay, so this is my vector. This is my cross product vector AB cross AD. Now to find the area of the parallelogram, I need to take the magnitude of this vector. And so I have the square root 0 squared plus 0 squared plus negative 16 squared. That's equal to 6. Let's try another parallelogram, this time in 3 dimensions. So we want to find the area of the parallelogram with vertices. We have K is 1, 2, 3. L is 1, 3, 6. M is 3, 8, 6. N is 3, 7, 3. Okay, so remember we fix one point and then we just create a vector to 2 others. Fix one point, a vector to 2 others. So we're going to do vector KL and KM. Vector KL, we have 1 minus 1 is 0. We have 3 minus 2 is 1. We have 6 minus 3 is 3. Vector Km, we have 3 minus 1 is 2. 8 minus 2 is 6. And then we have 6 minus 3 is 3. Now I just need the magnitude of the cross product of these 2 vectors. So let's first calculate the cross product. KL cross KM is equal to, we have IJK 0, 1, 3, 2, 6, 3. All right, this is equal to, we have I times a 2 by 2 determinant. What's going to be this 2 by 2? What are the entries for this 2 by 2 determinant? Red, first row, second row. Perfect. Awesome. Yeah, we have 1, 3, 6, 3 minus J times, help me out, what is it? 0, 3, 2, 3. And the last one? 0, 2, 6. Very good. All right, so yeah, just taking this determinant, we have I times, we have 3 minus, that's 18, minus J times 0 minus 6 plus K times 0 minus 2. This is going to be negative 15, negative 6, negative 2. Okay, so that's our cross product. All we have to do is take the magnitude of this bad boy and then we're good. So the magnitude, negative 15, 6, negative 2, is equal to the square root, negative 15 squared, plus 6 squared, plus negative 2 squared. Square root of 15 is 225. Plus squared is 36. Negative 2 squared is 4. So this is 40. We have 40 plus 226. That's the square root of 265. And this is the answer. Of the parallelogram. Okay. Another application of the cross product is something called the triple scalar product, and it looks like this. We have the triple scalar product. If we have three vectors, the triple scalar product denoted A dot B cross C. All we do, the only thing that's different is instead of IJK in the first row, we put A1, A2, A3. And then the rest is just like normal, B1, B2, B3, C1, C2, C3. So what's the output of this going to be? What is it going to look like? Yep, it's a scalar. So this is like some straight linear algebra. This is just taking a determinant. Take a determinant with all numbers, we get a scalar as the output. All right. So given three vectors, the triple scalar product also finds the volume of a parallelepiped. So, right, a parallelepiped being a 3D parallelogram. So, if we have, I want to see how this question was worded exactly. It says, find the volume of the parallelepiped determined by the vectors A, B, and C. So if they give us vector A being 1, 2, 3, vector B being negative 1, 1, and vector C being 2, 1, 4, then the volume of the parallelepiped will be A dot B cross C, which is equal to 1, 2, 3, negative 1, 1, 2, 2, 1, 4. So this is going to be 1 times a 2 by 2 determinant, 1, 2, 1, 4. We subtract off 2 times another determinant, and this determinant is going to be negative 1, 2, 4, plus 3 times negative 1, 1, 2, 1. All right, so we have 1 times 4 minus 2, minus 2 times negative 4 minus 4. And then we have plus 3 times negative 1 minus 2. So this is -8 right here, but we have -8 times -2. So this would be a plus 16 in the middle. 1 times 4 minus 2 is just going to be 2. And this is 3 times +3 is -9. This is 18 minus 9. The volume is 9. All right. The next topic we are going to discuss. Yep, gives volume. This is units cubed. Yeah, triple scalar magnitude of the cross product would give us the area of a parallelogram. But this is a parallelepiped. This is 3D shape. Yeah. All right, so let us talk about lines. You take the absolute value. Yeah, if we get a negative number, you would just take the absolute value. Good question. Alrighty. Yeah, we can't have negative volume, can we? No, unfortunately not. As much as I would like. I'm totally kidding. Anyway, so we have lines. We have 3 different types of equations that I'm going to talk about for lines. We have a vector equation. We have a parametric equation. And then we have symmetric. And you'll find that they're pretty much all the same thing, just written in different forms. So if we have, this is in R3, of course. If we have our z-axis, our x-axis, and our y-axis, then, and we have a line traveling through space. The vector equation will be r of t equals r naught plus t times v. Okay, let's analyze this. In 2 dimensions, we have y is equal to ms plus b. These are essentially the same thing. If we look at this r naught as being the y-intercept, but really it's just some point. R naught is a point on the line. So like R naught would be right here, for instance. And then we have m being the slope. Well, now we have a slope vector, v. And then x being the variable, t being the variable. But what t represents is a scaling of a vector v. So if we have this point r naught, then tv, vector t or t times vector v is just going to be a scaling of vector v, this vector. And so it could stretch it like this far, or it could stretch it a little bit further, or it could stretch it in the backwards direction if it was negative. Regardless, it's just some scaling of the slope vector. So it like stretches it or shrinks it. And what do you notice about if we add these two vectors using the triangle? Right, they're tip to tail, aren't they? Well, since they're tip to tail, we can go ahead and do the triangle. Right, and so really this vector that I just drew, r, is this guy. And so it's like this vector, after we do this vector addition, this vector points to the point on the line that we're discussing. Okay. Now, parametric equations. The parametric equation of a line would be x equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. If we solve all of these for t, what they have in common, well, for the first one, we would get x minus x naught over a equals t. For the second one, we would get y minus y naught over b equals t. And then z minus z naught over c equals t. And then since t equals t, right, they're all the same t, aren't they? We can equate them to each other. We have x minus x naught over a equals y minus y naught over b equals z minus z naught over c. Now we have the symmetric equation for a line. So this is parametric, symmetric, and then we have the vector equation. Now, if we call the point r naught in the vector equation, so I want to rewrite it down here, r of t equals r naught plus t times v. So if r naught is it's a point, we call it, like x naught, y naught, z naught. And then the slope vector we denote as ABC. Then we're multiplying, t times v. Really what this vector equation turns out to be is x naught, y naught, z naught plus ta, tb, tc. And then we could add these two vectors. We have x naught plus at, y naught plus bt, and then z naught plus c. Notice that's the same thing as the parametric equation. They're all really the same. All right. So let's work an example. Let us, where's my pen? Okay. Find the vector equation and parametric equation of the line through the point 2, 2.4, 3.5, and parallel to the vector 3i plus 2j minus k. All right. So let's first find the vector equation. Remember, let's write our formula down. R of t equals R naught plus t times v. Now, all of this is really given. We just have to, decode the words. This point, it passes through this point, so that's going to be our R naught. Parallel to the vector, 3i plus 2j minus k, just means that this can be our slope vector. B. So writing the answer, just straight up, we have 2, 2.4, 3.5, plus t times 3, 2, negative 1. Now, in parametric form, we would have x is equal to 2 plus 3t, y is equal to 2.4 plus 2t, and z is equal to 3.5 minus t, right? 2, 2, 3t, 3t, 2.4, 2.4, 2t, 2t, right? You see the pattern. 3.5, negative t, 3.5, negative t. Now, if we were to find the symmetric equation, right, we would just solve for t in all of these and equate them. Okay, so this problem is analogous to the two-dimensional case where we're given like a point in the slope, right? We have one point in the slope, thus we can find a line passing through this point with that slope. Now, another case that that comes up in these algebra classes or whatever, if they give you 2 points. So let's find vector parameterization. Yeah, so t would be like the scaling of the slope vector. So look right here. If we have t is like the variable. It would stretch, if we made t bigger, it would stretch it further, and then we would just get to like a further point on the line. So yeah, it stretches the length of it. Cool. So we need to find the vector parameterization of the line through the points P naught and P1. So 2 points, and they don't give us slope. They don't give us the slope because we can find the slope. The slope vector, the v vector, is just going to be the vector P naught, P1. And then we can pick either P naught or P1 for the point passing through, because remember our vector equation is R of t equals R naught plus VT. So we can pick either P1 or P2 right here, and for V, we have P naught, P1. So calculating vector P naught, P1, we have 3 minus 8 is 11. Negative 2 minus 1 is negative 3. 4 minus 4 is 0. R of t equals, I'm going to use P naught for R naught. We have negative 8, 1, 4 plus t times vector v being our slope vector, what we had to calculate this time, 11, negative 3, 0. Is the point 14, negative 5, 4 on the line? How do we determine that? We make the x, y, z slope equations. What do you mean by that? The previous problem. Oh, and the parametric? You're talking about the parametric form. This is x minus x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. Yeah, this is called parametric equation. Yeah, we can do that. I think that's a good idea. So what would x be in this case? For the parametric equation, it would be, x naught plus at. Remember the point r naught, which is right here, is analogous to, negative 8. And then we plus at. You got the x naught all right, but what's the plus at? Up here we have plus, there you go, plus 11t. And then what is y? There you go, dude. Z equals. Cool. So how do we determine if this point is on the line? We could call this point, if this was x naught, y naught, z naught, this point could be x, y, z. Now what I'm going to do is equate the x component. Yep. See if the t is equal. Yeah, very good. So we have, what do we have? We have 14 equals negative 8 plus 11t. And then we have negative 5 equals negative 1 minus 3. Yeah, and then z equals, we have 4 equals 4. It's not writing. We have 4 equals 4 for the z, so that checks out. This is our x, and this is our y. So let's solve for t, and if t is equal to t, then we're good. Plus 8 plus 8. So what is that? 14 plus 8 is, that's 6, and then another 2, so that's going to be 2 is equal to 11t. So that means that t is equal to 2. This should be a positive. Should be a positive 1. Right? Yeah. Positive 1. This should be a positive 1. Subtract 1, subtract 1. These cancel. Negative 6 is equal to negative 3t. T is equal to negative 6 divided by negative 3 is positive 2. So we got t equals 2, t equals 2, and 4 equals 4. That checks out. Thus, the point is on the line. Okay. Is the point negative 8, 1, 5 on the line? No. Immediately, we can tell. Yeah, z equals 5. The z component should always equal 4 on this line because the slope vector is 0 with the z. But since this is equal to 5, we would have 4 equals 5. Not true. Thus, this point is not on the line. Okay? Now I'm going to ask you another question. Does the line pass through the xy plane? Where? Yep, it does not. Yep, z is always 4. Yeah, that was basically the same question, right? You said, right, z is always 4, and f equals 5. Z is equal to 4 constant in our line. So that means that z does not equal 0 ever, which would have to happen if we were on the xy plane. We're going to do one more problem, and then see how long this takes, and something about planes. So we need the parameterization of the line through the point 2, 1, 0 and perpendicular to both I plus j and j plus k. This line through 2, 1, 0 and perpendicular to both I plus j and j plus k. Well, to find a vector that's perpendicular to I plus j and j plus k, this is the cross product. So let's go ahead and calculate that. We have I, j, k, 1, 1, 0. That's this vector. And this vector is 0, 1, 1. So this guy, we have I times 1 minus 0 minus j times, cross out j, we have 1 minus 0 again, plus k times, crossing out this guy and this guy, we have 1 minus 0. So this is going to be 1, negative 1, positive 1. But what is this vector? Well, how does that even relate to my problem? So we have a line, we have a point, and then we want the line that's perpendicular to both I plus j and j plus k. So is this line going to be Yeah, point vector plus vector times time. What's the point vector? Yep. And then we have plus t times what vector? Very good. Like a pro. Awesome. That's it. That's the answer. Yeah. If it's perpendicular to both this vector and this vector, then that means it's parallel to the cross product of these two vectors. And thus, if we have vector parallel to our line, that's going to be our slope vector. Yep. So that's the parameterization. And then we could ask, where does this cross the xy plane? We cross the xy plane when z equals 0. Oh, well, immediately we would find r of 0 equals 2, 1, 0 plus the 0 vector. That's where it crosses the xy plane. That was kind of a dumb question on my part, but yeah. They might ask you some other questions about these lines. They might say, okay, where does it pass through the y-axis or something like that. All right. So we got 10 minutes left. Are there any questions, first of all? Any questions? When does it pass the xz plane? Yeah, that's a good question. So let's look at the xz plane. So this is the z-axis, this is the x-axis, this is the y-axis. This is the xz plane. So what's so special about the xz plane? What is y doing when we're on the xz plane? Well, y is 0 on the xz. Yep, that's true. You got it. Y is 0 on the xz plane. On the xy plane, the z would be 0. On the yz plane, x would be 0. So we have to find t such that I equals 0 in our parametric equation. Can you think of what t might be? R of what value t would yield a 0 in this component? Yeah, you can do it like that. Yeah, exactly. T equals 1. Very good. So we have 2, 1, 0 plus 1 times 1, negative 1, 1. So this is equal to 2 plus 1, 3. And then we get 0 like we should. 1 minus 1 is 0. And then we have 0 plus 1. So this is the point at which it crosses the xz plane. Awesome. Any other questions? All right. So with planes, they take the form of ax plus by plus cz equals d. This is like the standard form of a plane, where the vector abc is perpendicular to the plane. So you can imagine you're going to be taking a lot of cross products. To find D, really what you do is you do You do A, B, C, the vector that's perpendicular to the plane, dot product with x minus x naught, y minus y naught, z minus z naught, and it equals 0 because they're perpendicular. And then you would find, well, do the component-wise multiplication of this dot product. We have a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Then you multiply all this out, collect all the constants, and that would be d. So a common problem, they give you 3 points and say find the plane passing through or containing these. You fix 1 point, you fix the other point, and then you take the cross product. And the cross product would be P naught P1 cross P naught P2. That's your ABC vector. That's sort of like a slope vector, but it's not parallel this time. It's perpendicular. So I guess I'm going to stop it right there. I'll pull some examples, some examples about planes next time. But I'm going to end it right there. Thanks for showing up, taking part in your own education.